Hello, everybody. Thank you for joining NTT ION technical workshop session. This time, we invited four speakers from NTT laboratories. They'll introduce the latest ION technology. The first speaker is Masahiro Nakagawa, Associate Distinguished Researcher, NTT Network Service System Laboratories. The title is a recent progress in ION APN use case and enabling technology development. Mr. Nakagawa, floor is yours.
Okay, thank you for the introduction. Good afternoon, everyone. I'm Masahiro Nakagawa from NTT. First of all, I'd like to thank committee members for giving this opportunity to introduce our activity. So today, I'll talk about the recent progress in ION all photonics network that covers use cases and enabling technologies. So here is an outline of my talk. This talk mainly consists of general background, ION description, and its use cases, as well as key enablers. So let me start with some background. So due to the bandwidth-intensive applications and increasing in the connected devices, data volume is continuously increasing throughout the world. These are such examples. Namely super high definition video, 3D video, immersive experiences, and billions of IoT devices. These push data volume increase. In such a data-rich world, the power consumption issue will become more apparent. This figure shows the forecast of power consumption of data centers. This means that we will face dramatic increase in power consumption. So in addition, several emerging services are being developed. In general, such advanced services have specific latency requirement, like less than a few milliseconds. For deploying any services nationwide, reduction of network latency is essential. Moreover, in the beyond 5G or 6G era, it is expected that cyber-physical systems will enrich our daily lives. In such a situation, IoT and AI-related communication will become more common, where a huge amount of data is unconsciously exchanged in a real-time fashion. Hence, network operators must carefully consider data volume, power consumption, and latency issues. To address these critical issues, NTT has proposed ION concept. So ION stands for Innovative Optical and Wireless Network. Its target performance are listed here. Let's say extremely low power consumption, extremely high capacity, and extremely low latency. So what is ION? So it is a communication platform that realizes a smart world by using three elements of all photonics network, digital twin computing, and cognitive foundation. In addition, photonics electronics convergence technologies are applied to processors that will be presented in this session. So this talk will focus on all photonics network. The key idea behind this game-changing infrastructure is from electronics to photonics. So let me now introduce APN overview and its use cases. This slide highlights the difference between today's transport network and APN. In traditional TCP/IP-based network, many users' data are terminated at each network domain or segment, and IP routers handle such data. So in this architecture, although optical paths can be shared by many users, it is difficult to support deterministic quality of service in terms of bounded and lower latency. So on the other hand, in APN, unrequired termination and electronic processing are eliminated, aiming to provide end-to-end lambda connections. Such connections enable each user to enjoy a high-quality communication environment exclusively, and latency experienced by each user can be bounded or deterministic. Moreover, power consumption of routers depends on the bitrate and the number of interfaces. This severely limits energy per bit performance. On the other hand, photonics-based technologies inherently have the potential of bitrate agnostic operation. So this offers huge benefits in terms of energy efficiency. Okay, so since APN can provide an exceptional communication environment, as I mentioned, APN enables various use cases. They include data center transformation, further enrichment of remote activities, and smart society realization. These can lead to various business opportunities. So hereafter, I'll present several use cases. The first example is a distributed data center operation. So as you know, data centers are now crucial, and centralized hyperscale data centers have been common so far. However, mainly due to energy and space issues, decentralization of data centers is being actively discussed. Such issue will be maybe discussed in the next presentation. So this centralization of data center is how to say important topic. So there is a solid opportunity for distributed data center operation interconnected by the APN. So in particular, APN enables to build virtual large data center in an agile manner. And this solution has good expandability and flexibility. For instance, by connecting additional data centers to APN, the total resources can be easily scaled. Unlike conventional solutions, this does not require individual dark fiber connection to each existing data center. So it is also possible to relocate workload according to renewable energy balance. This leads to green solution. Okay, this is our first example. The second is a remote media production for broadcasting industry. The left-hand figure shows the current solution, that is local production. In this case, broadcasting vehicles and staff must be required for each location. This has potential issues for operation. That will be not sustainable. On the other hand, APN enables full remote production, and the need to dispatch variable resources to the camera shooting site can be eliminated. Recent proof of concept experiments demonstrated high definition uncompressed video transmission from 15 cameras and camera control with about 30 milliseconds between distant locations. Okay. The third one is a cloud endoscopy system in the context of smart medical care. These figures show a comparison between current and cloud system with APN. So as shown in above figure, the current system is based on user premises devices and local processing. This has potential issues of performance limitations and maintainability. So to overcome issues, IPN can be used for real-time diagnosis and treatment on a remote server. This can lead to the world's first cloud system. Moreover, recent tests have proved its feasibility, specifically image processing between device and server separated by 150 kilometers. Okay, these are use cases. So let me turn to key technologies, especially optical node systems. Again, this is a comparison between today's network and APN. In addition, key concept is providing end-to-end lambda connections, as I mentioned. So APN mainly consists of optical transceivers, photonic exchanges, and photonic gateways. Here, photonic exchanges and photonic gateways are novel optical nodes, and they are key enablers. As these nodes handle user signal in the optical layer, end-to-end lambda connections are set up and deterministic performance can be achieved. More specifically, for providing end-to-end lambda connections, capacity scaling and limiting factor mitigation must be required. As you can see, when the number of transceivers are increased, photonic exchanges must handle numerous lambdas in an efficient manner. Moreover, admission control and several gateway functions must be provided within photonic gateways for freely deploying transceivers at the user sites. So hereafter, I'll introduce overview of these two node systems. First, I'll present the overview and key functions of photonic exchanges. So as I mentioned, for providing APN services nationwide, numerous connections must be handled in an efficient manner in the optical layer. So photonic exchanges have wavelength cross-connect as a fundamental function of optical nodes. Moreover, not only large capacity, but also excellent flexibility is required from network operator perspective. Actually, there are large variations in physical layer attributes of transport networks, such as optical fiber type and wavelength specifications of optical systems. Such differences are limiting factors or barriers to true end-to-end lambda connections. To mitigate these factors, we are trying to apply two types of wavelength conversion. Traditionally, optical wavelengths cannot be changed without optical electrical conversion. Such optical electrical conversion can be cause of latency and power consumption. So for achieving flexible wavelength utilization and low latency as well as low power consumption, two types of wavelength conversion treated as the key functions. Okay, the first one is PPLN-based interval wavelength conversion. PPLN stands for periodically pooled lithium niobate, and this is an NTT's cutting-edge device. This enables wavelength band of optical signals to be changed to another simultaneously. So we are investigating its feasibility by prototyping photonic exchanges utilizing such devices. Right-hand figure is photo of our prototype, and we have conducted several experiments. So the other is OAO wavelength conversion. OAO means optical analog optical, and digital signal processing is eliminated through wavelength conversion process. Similarly, we have prototyped this system and feasibility has been demonstrated. So for more details, please see a press release that has recently published. Okay. The second node system is a photonic gateway. This is a advanced optical node system providing gateway function at APN entrances. So due to the time limitation, this talk will focus on remote transceiver control. So this is the in-channel remote transceiver control function. That is the important function to deploy transceivers to user sites freely. In other words, no limitations is required. So this is essential for flexibly placing transceivers and enables various transceivers to be connected. Okay, so in this talk, I presented critical challenges and ion APN description. And I presented overview of optical node systems as key enablers, that is, namely photonic exchanges and photonic gateways. So this concludes my talk. Thank you for your attention.
Thank you very much. Is there any question on the floor? You don't have? Okay.
Thank you for your interesting talk. I have a question about migration from current legacy network to APN. I mean, what is the motivation for a carrier or private company to migrate from legacy network to APN?
Okay, thank you for your question. So that is a very good point. So how to say, how to migrate from a current network to APN is itself is a discussion point. So that is how to say good need further discussion. However, our motivation is based on the general background part. So basically, the current TCP/IP-based network is no longer sustainable for near future world where data volume is increasing, and stringent latency requirements must be required. So our solution, ION, is presented. That is basic general background.
Thank you. Thank you very much.
Okay. Any other question on the floor?
Sorry, I'm also from NTT, but I have a question about OAO technologies. Is there any necessity to use analog signal? I mean, can you change the signal directly to optical? So why do you need analog signal in that case?
Okay, thank you for your question. Thank you for your question. So this is the, how to say, what we call short-term solution to wavelength conversion. So I mean, these are two types of wavelength converter. The left one is the all optical type and the simultaneous conversion of whole band to another. So that is relatively difficult to test or validate its performance and operationability and the production perspective. So, however, the second one is OAO. That is the, how to say, once converted to electrical analog domain. That is relatively easy to implement. So that is short-term solution.
Thank you very much. Any other question on the floor? Okay. Thank you very much, Nagawa-san.
Thank you.
Okay, next speaker is Hideki Nishizawa from NTT Network Innovation Laboratories. And his title is Automatic Network Operation based on the optical network digital twin.
Okay. Thank you for your introduction. So I'm Hideki Nishizawa of NTT Network Innovation Laboratories. I'm also working as a coordinator of ION Global Forum Open APN Task Force and the co-leader of TIP OPT disaggregated optical systems. So it's a great honor to make a presentation at this conference. Thank you very much for organizer. So today's my talk is like this. First one, the title, automatic operation. So what automatic operation offer to optical networks? And then I want to talk about the requirement for commercial implementation. And then a key enabler for optical network digital twin. Physical modeling and open interface and open source software is very key to realize these features. And then I want to summarize my talk. Already the first speaker, Nakaga-san, introduced what's OpenAPN. So with this slide, let me explain what's the most important point of OpenAPN. So you can see that on the top of this architecture, you can see a digital twin net computing region. On the bottom side, there is very many terminals. So this device terminal, maybe a human, we are connected to the other side directly. So lower power, lower latency, and the big bandwidth want to connect directly. So current network cannot provide these services. Later, I want to explain why current network cannot provide with other slides. And here, ION OpenAPN task force team are discussing how we can design the goal of OpenAPN. So keyword is end-to-end lambda connection and dynamic optical path provisioning control. And the computing and networking convergence are also important. So today's my talk focusing on this one, and also you know that recently automatic operation, digital twin, machine learning. This keyword is a very used by many presenter. So from the ION point of view, I want to talk what we can use such a latest technology to optical networking operation. So that's my talk. So I have summarized 3 points. What can automatic operation offer to optical networks? First one is service. Switching from traditional point-to-point fixed connection services to multi-point lambda connection services. So first, the presenter said remote production and data center interconnect. So these are multi-point lambda connection services. And the operation side, provisioning, optimization, and failure recovery operation from a different time zone. So this is also very important. Later, I want to explain the with figure. And the convergence, realizing the highly reliable and flexible infrastructure through integrating computing and networking. So these 3 benefits we can have with automatic operation. So first one, multi-point connection services. I have described the image of data center exchange. So as Nakaga-san said, so distributed data center is one of our feature. And just a minute. Yeah, here is a data center. And because of power supply issue in metro area, recently we needed to build a data center in neighboring prefecture. So in this case, we needed to connect the data center to data center directly. But as Nakagawa-san said, so latency is very limited. So latency requirement is very key. So for example, hyperscaler generally limit the 100 kilometer because computer-to-computer communication require very low latency. So ideally, we want to connect the data center to data center in the different prefecture. So we want to provide a new type of multi-point connection services. So within the ION Global Forum, we are now discussing how we can realize these network services. So we have already developed a new documents such as ION OpenAPN functional architecture document and network digital twin document. The key feature is a failure detection. So we connect the end user side directly without optical and electrical optical conversion. That means we need to know that what's happened at the optical network. So the failure detection, new failure detection technology is a very key. And also QoT estimation is a very important because when we connect the user data center, may go through user access line. So NTT don't know the quality of user access line. So definitely such a QoT estimation is a very key feature for us. So let me introduce this issue. So conventional network architecture, I want to introduce two type of one. So left-hand side is a layered ring architecture. So generally, carrier network provided with this one. So every prefecture have a ring network. And a ring network connected with ROADM. And this ring network is layered. So when we go through long distance, in this case, we will go up to upper layer. So this is a very good architecture, and for a long time, this network architecture supported many services such as FTTH and mobile. So human-to-human communication, this network have supported. But short point is latency. So here is a data center and data center, but this one may need to go through a long distance. So this is a short point of this architecture. So right-hand side is a routed hub and spoke type of network. So recently, router can have a coherent module. So connecting router with coherent module, we can provide a data center interconnect services. But the short point of this network is a risk will be in here. So network concentration risk and the power supply heat redundancy risk in here. So I have to say that expansion is not good. Reliability also not good. But maybe latency is good. But if router capacity is not good enough, or latency also not good. So we need new architecture. So I have tried to describe the advantage of data center exchange. So this data center exchange is discussed among the OpenAPN task force team. So connecting user data center to the other data center, and also cloud A, cloud B, MEC A, MEC B. So want to connect directly with optical path. So using the ROADM system, we can connect each side with wavelengths. So expansion is very good because of using the ROADM system, and the reliability also may be able to, because so for example, this blue line, lambda 3, if we have some issue, we can switch the path. So on the other hand, sure, we need automatic operation and very quickly recover the failure. So on-demand optical wavelength WDM path provisioning reroute. And these technology will be required for new architecture. Latency is very good because so connect the data center to data center directly. Don't use the ring architecture and the layered architecture. Multi-vendor and multi-generation transceiver accommodation also will be required because so we need to connect many customers and also QoT unknown access line. So this cloud mean the access line. So we need to know the quality of this one. So we have to develop a new technology for automation. And later, I want to introduce our challenge with digital twin technology. And the second benefit is operation from a different time zone. So operation side issue is that the number of optical engineer is relatively small. So when we provide an open APN service all over the world, in this case, most critical issue is a short of engineering. So our idea is using the digital twin technology, operators can perform provisioning, optimization, and failure recovery operations using visualization and software control technology. So our idea is from a real environment is nighttime. So gather fiber data, amplifier data, ROADM data. We collected these data and optimized, analyzed, then send these data to, for example, in Japan. So real environment in US, virtual environment maybe in Japan. So we can design in a different time zone. So these also automation benefit from automation and digital twin technology. The third one is integrating computing and networking. So within the data centers, hardware, software disaggregation technologies such as server, storage, virtualization have advanced. So for example, in Japan, Line and Yahoo, so these hyperscaler develop thousands of systems within several hours using the automation technology, open source software such as Zabbix and OpenConfig and Ansible. So on the other hand, as for the optical side, under layer one, it's a monolithic, so very vendor proprietary system. So once we can we can realize this aggregated technology for layer one and layer zero, we can automate everything. So data center and inter-data center. So once we can have such a technology, we will be able to provide a much more rich services. For example, redundancy. So leveraging the power demand density by connecting data centers. So in Tokyo, already power supply is shorted. So we can dispatch to, to distribute the data center to other site where we can provide much more power. Okay, so next page is requirement for commercial implementation. So adaptability to conventional methods is very important. So the existing trained workforce and the established technical practice are adapted to traditional network methods. So these function within the OA task force we are discussing. And the next one, transparency and explainability. So this network is a infrastructure. So definitely, a carrier need to show explainability. So we have to guarantee SLA. So second point is this one. And the third point is cost constructions. So we don't have to increase the number of equipment, hardware. So reduce the cost and then provide low latency and big bandwidth service to customer. And the last one is generalizability. So if methods or models are sensitive to changing in data or the device type, vendor, because of temporal variation or link modifications, then they cannot be applied in dynamic, diverse, wide area network scenario. So these 4 points, we think these are requirements for commercial implementation. And then key enabler, we think that it's a key, with this slide, please let me introduce the key enabler for optical network digital twin. The first one is physical model. So we needed to modeling the physical layer. So fiber and amplifier, load system also. So we are collaborating with Euro region major universities such as Porto University for several years. And then we are now providing some models to academic conferences. And then last year, we have succeeded to do testing from between the United States, Duke University, and Japan, our lab in Yokosuka. So digital twin approach, we have started to try. So here, very important point is the open interface. So from different time zone, we need to manage the equipment and we need to design the optical path. So the, for example, optical path design tool must be an open tool. And also interface should be open. So then we can manage the every type of vendor equipment. So last part of my presentation, let me introduce our latest activity. So for example, visualization of fiber optical link. So NTT have introduced digital longitudinal monitoring technology. So this is a very new technology. So conventionally, OTDR is a very major to measure optical path power profile. This technology can go through amplifier and also without putting the new hardware, we can measure with current coherent transceiver. So this is a very new technology and recently introduced to conferences. So this new technology, without increased equipment, then we can measure the fiber parameter. And the next one is visualization of EDFA characteristics. So this technology itself is introduced by NEC Laboratories America. So you know that WDM is very difficult to manage the chilled issue. So EDFA gain, NF, is depend on the wavelengths. So how we can optimize the multi-layer amplifier. So we have applied a new technology and we can optimize these amplifier without using the vendor proprietary technology. So on this testing, we have used Duke University test bed of field fiber, and within 1 hour, we could optimize the optical link. So if you are interested, please access to my paper. So these new technology we have developed and introduced, and then summary, automatic network operation will accelerate multi-point lambda connection services such as data center exchange and operation from different time zone, and then integration of computing and networking. So, and the next one, requirements for commercial implementation. So adaptability to conventional methods, transparency and explainability, cost constraints, and generalizability. Key enabler is a physical modeling and open interface and open source software. Thank you for your attention.
Thank you very much, Nishizawa-san. Is there any question from the floor? Maybe you will have later. Okay, thank you very much. Okay, thank you very much, Sasa-san. So next speaker is Fumiaki Kudo-san, Senior Research Engineer, NTT Social Information Laboratories. His title is Encrypted Communication Technology for Quantum Computer Era. Are you ready?
Yes.
Okay, praise you.
Thank you for your introduction. Hello, everyone. My name is Fumiaki Kudo from NTT Social Informatics Laboratories. Firstly, thank you for this opportunity to be here. Today, I'd like to talk about quantum-safe encrypted communication technology for future networks. My presentation is divided into 4 parts. Firstly, I will explain the need for post-quantum security in the future networks. And then I will introduce NTT technology called post-quantum secure transport. And after that, I will also introduce our POC using post-quantum secure transport and international APN. And finally, I'd like to present future prospects for end-to-end data security with this post-quantum secure transport. Okay, let me begin by explaining the need for post-quantum security in the future networks. This is a motivation. It is that a practical quantum computer will appear in the near future. And compared to existing computers, quantum computers are expected to greatly improve performance in certain calculations. And so in the field of security, cryptography, it is said quantum computers are said to be a great threat. And for example, NIST in the US states that if large-scale quantum computers are built, they will be able to break many of the public key crypto systems currently in use. Okay, then how exactly will existing cryptography will be affected? There are 2 major types of cryptography. Public key cryptography and symmetric key cryptography. And it is said public key cryptography in particular will be greatly affected. When a large-scale quantum computer is completed, RSA and elliptic curve cryptography using existing key exchange system and a signature system will be broken in a realistic time by quantum algorithms. So we need to migrate current public key cryptography to post-quantum public key cryptography. And now various organizations are currently standardizing PQC, post-quantum cryptography. Among organizations leading the way is NIST in the US. And the NIST PQC competition is still ongoing, but first, several PQC algorithms were selected, and several standardization documents have been published last year. And I think your biggest concern is when should we transition to PQC? The answer to this question is that we need to begin a transition to PQC as soon as possible because a transition of crypto system takes a long time. In fact, specific recommendations have been made in several countries and regions. For example, US and Korea have set a goal of completing the transition of their national security system by 2035. And another important aspect of transition to PQC is concept of crypt agility proposed by NIST. The PQC is a technology with a short history, so it is possible that an efficient attack could be found suddenly for either algorithms. One of the solutions for this issue is a hybrid scheme standardized in several organizations. The basic idea of hybrid scheme is using multiple cryptographic algorithms at the same time so that we can maintain a certain level of security even if one of them is compromised suddenly. And based on this hybrid scheme, we NTT have developed quantum-safe encrypted communication technology. But then I will introduce NTT technology called post-quantum secure transport. And this technology, post-quantum secure transport, can provide point-to-point secure communication with high crypt agility without compromising network performance. The network incorporating this technology can always keep security even against quantum computers with our original hybrid key exchange architecture. Okay. This slide shows the architecture of post-quantum secure transport. This architecture can perform multiple key exchange algorithms at the same time and obtained multiple keys from multiple key exchange algorithms combined to generate the encryption keys. And these encryption keys are provided to encryption application such as MagSec. And this architecture has two major features. First one is this technology enables flexible combination of different types of key exchange algorithms, including PQC, PQC-Chem, and a rapid switching of them without stopping communication. And second one is this technology can be implemented on various environments because of its disaggregated architecture. This is a configuration variation of this technology. This technology can be implemented on a white box transponder independent of network OS, because of its disaggregated architecture. And then, in addition to this, this technology can be also implemented on Linux VM directory. The scope of encryption is different for either implementation. This configuration variation, we believe, can meet various needs for the quantum-safe encrypted communication. Okay, and next, I will introduce the POC using this technology implemented on white box transponder. We demonstrated the data replication between Taiwan and Japan, distant 3,000 kilometers away. We believe all photonic network would shorten the data replication time between distant data centers, making it possible to ensure their BCP. And in this POC, we demonstrated the faster synchronous data replication using international APN with our post-quantum secure transport. This is a result of the test without post-quantum secure transport first. We tested the data replication using data assumed financial use case. It consists of a lot of small files. We verified APN can dramatically reduce the replication completion time compared to existing IP networks. And then we tested the data replication with post-quantum secure transport to protect data between two storages. And this is that configuration. We installed a white box transponder called Galileo Flex T or GFT, implemented our post-quantum secure transport into the network in front of the storages. And this configuration can achieve the quantum safe encrypted communication between Galileo Flex T. And this is a result of the test with post-quantum secure transport. We verified the replication completion time with and without post-quantum secure transport is almost the same. Now we can say the difference between them is within a margin of error of storage performance. Okay, lastly, I'd like to present the future prospects for end-to-end data security using this post-quantum secure transport. This is the NTT vision for end-to-end data security over ion APN. And we believe the APN or photonic network enables distributed computing and disaggregated computing even across the distant data centers. To promote active collaboration on this ion APN, we aim to create secure data space across data centers that can maintain data sovereignty throughout data lifecycle, and not only data at rest and data in motion, but also all states of data, including data in use. This is our vision for end-to-end data security. And to achieve this secure data space over APN, we believe we can use our technology implemented on confidential VM using Trusted Execution Environment or TEE. This slide shows one use case of APN, a remote GPU over APN, which is discussed as one of promising APN use cases. In this use case, calculations are performed on GPU resources in a green data center using data remotely over APN in user site. And the basic idea of end-to-end data security in this use case is that we put the confidential computing spaces using TEE in both sites. And these confidential computing spaces are connected to each other directly with post-quantum secure transport. We believe this seamless, secure connection between confidential computing spaces and TEE-enabled GPU product will enable the end-to-end data security from storage to GPU without compromising APN performance. Yeah, this is an example of our vision for end-to-end data security over APN. Okay, this is last slide of my presentation. The main points of my presentation were that we must begin transition to PQC today. And NTT's post-quantum secure transport can provide secure communication against quantum computers with high cryptography without compromising APN performance. And NTT is aiming for creating secure and high-performance data space over APN with post-quantum secure transport. That's it. Thank you for your attention.
Thank you very much, Kudo-san. Is there any question on the floor? Okay. So thank you very much, Kudo-san. So I'd like to move to our next speaker. And if you have a question, please contact directly.
Thank you very much.
Okay, last speaker from NTT is Yuzo Sakai-san, Director of Optical Interconnect Device Project, NTT Device Innovation Center. His presentation title is Photonic Electronic Convergence PEC Device Technology for ION.
Okay, I'm ready. Okay, thank you for your introduction. Good afternoon, everyone, almost evening. And my name is Yuzo Sasaki from Device Innovation Center of NTT. Today, I'm very pleased to present our recent topic of device technology that we are developing recent years. Here, this is the vision of ION, but it's already presented previous presentation, so I almost skipped this slide, but I only mentioned the three targets of ION. One is high quality and high capacity, low latency, and low power consumption. So in my talk, I mainly introduced the device technology, which includes the photonics electronics convergence. We call this PEC, that we have been researching for these years. This figure shows that transition from the electrical to optical transmission. The vertical axis presents a range of data transmission speeds from 10 meg to 100 terabit per second. For the horizontal axis, distance varying from 1 centimeter to 1,000 kilometers. As for the low capacity and short distance, the electrical data transition has been used historically. The optical technologies have been adapted for long distance and high capacity data transition. In the range of short distance, it's better to use light here to increase the speed even over short range. You can see the reason why we use the optical transmission here. Even if the transmission distance or transmission frequency is increased, the power consumption of the optical transmission is very small compared with that of electrical transmission. But the technological transition is driven by multiple factors, including not only performance, but also cost, related technologies, and the maturity of the ecosystem. So next, let's take a look at the PEC device roadmap. So the PEC, photonics electronics convergence device, will evolve from 1 to 4 through the step aligned with the ION roadmap. Of course, there is technology advancement, but we distinguish between these generations on their areas of applications. Currently, we have launched PEC-1, which is designed for long-haul, metro, and data center interconnection. Looking ahead, the PEC-2 for board-to-board connection is scheduled to be introduced in this year. The future target of the PEC-3 and PEC-4 is the interpackages and die-to-die connection, respectively. So let's explain the PEC-1 first. I also can say the PEC-1 is designed for long-form metro data center interconnectors. So in the era of PEC-1, our device technology is used for optical transceiver. I introduced two examples of PEC-1 devices. One has the high capacity and high performance. The other is small size and low power consumption. But before explaining the example PEC-1 devices, let's look at the evolution of optical transmission capacity of telecommunication. From 1980s to 2020s, various technological innovation taking place, such as TDM, WDM, EDFA, and including digital coherent technology. Each time, transition capacity has increased dramatically. We, NTT, also have been developed various devices to realize such communication methods. For example, lasers as a light emitting elements, the amplifier or switches for controlling optical signals. And in addition to optical devices, electrical devices for processing electrical signals here have been also developed at the same time. So here I'm showing the coherent modulator technology in optical device as a PEC-1 device. So the highlight of this achievement is a high transition capacity of 1.2 terabit per second per lambda. This technology was introduced in 2022 with a simple rate of 140 gigabaud. The key enablers here, including DSP, which includes these technologies. Of course, it includes the cutting-edge technology of 5 nanometer fabrication processes. Additionally, NTT's proprietary wide-ranging optical devices and newly structured package technology has contributed this result. The other topic of the PEC-1 device is the advancements in silicon photonics technology and its significance in advancing size reduction. This technology enabled the integration of this digital coherent transceiver and receiver into a single silicon chip. As you can see here, the silicon photonics chip as an optical component and TIA, driver, and DSP as an electrical components are integrated in a single package here with utilizing the high density electrical interface, EGA, as shown here. As a result, substantial miniaturization is achieved compared to traditional optical components devices, while simultaneously enhancing performance and reducing the power consumption. That's the PEC-1 devices. And let's move on to the PEC-2 to PEC-4 devices. As for the PEC-2, the PEC serves as optical engines for board-to-board connection. In the era of PEC-3 and PEC-4, optical chiplets are used for package interconnection and die-to-die connection, respectively. In that case, the transmission distance becomes shorter and shorter as generations progress. So one of our motivation to use optical data transmission in shorter distance is to establish optical disaggregated computer. Now let's see the concept of optical disaggregated computing. Let's say there are several computers or servers here for computing in traditional configuration. The data must be sent and received here over outside network of computers. So there are some limitations, for example, large latency, limited bandwidth, and so on. On the other hand, the approach of the disaggregated computing is designed for maximizing the power efficiency of computing servers. Each devices here is interconnected by high bandwidth, low latency optical communication technologies. As a result, the processing load on CPU is alleviated. So this capability is particularly beneficial for handling high demand computing, such as AI training. So here shows the one example of PEC2 devices. The optical engine is approximately 15 millimeter by 20 millimeter and has a broadcast capacity of 3.2 terabit per second in accordance with the specification of OIF. The OIF stands for Optical Internetworking Forum, which provides the worldwide standards of networking. Inside here, the silicon photonics and analog IC and DSP are integrated together with the fiber array unit. The optical fiber is connected here to connect outside the board. The ASIC and optical engine here is connected electrically on the motherboard. So there is some transmission losses of electrical signals. So it's effective to place the optical engines, these engines, as close to the ASIC switch as possible. So that's the reason for this configuration surrounding ASICs. So this is about PEC3. PEC3 is under development to be realized as an optical chiplet. This project is partially commissioned by NEDO. NEDO is a Japanese National Research and Development Agency. Within this project, we are advancing cutting-edge semiconductor technologies, including the photonic IC fabricated by the indium phosphide membrane photonics. It's lasers and modulators. Not only utilizing the feature of PIC, the hybrid integration of PIC and EIC with high-density packaging is key technology. So the semiconductor materials, indium phosphide itself is using multiple communication devices because of its high-speed characteristics. The advantage of the NTT's device is because of its thin layer. The membrane, thin lateral structure here, enable reduction of power and due to the large optical confinements. So let's see the conventional fabrication method. Semiconductor materials are vertically stacked, so it's difficult to confine the light efficiently. So on the other hand, our membrane has thin layer by fabricating semiconductor structure horizontally. So this allows us efficient operation resulting in low power consumption. This is a recent result of membrane photonics with 6-inch laser assembled in an array on a single chip. The chip size is only about 1 millimeter by 3 millimeter. We achieved 2 kilometer transmission of optical signal with 112 gigabit per second for all these 60 lasers. So this is a concept image here. Is PIC device connected to the semiconductor dies and transmitting optical signal by membrane PIC. So this is the actual photograph of the device. This device consists of 3 components: electrical IC for driver, photonic IC for other laser, and optical fibers. The cooperative design of EIC and PIC here is important for reducing power consumption. And even if the combination of EIC and PIC is highly efficient, overall power consumption will not be decreased if the light cannot be extracted efficiently. So the precise connection of the optical fiber array to the PLC is another important challenge that we are now trying. The final topic of my talk is about application example of optical chiplets. For training of generative AI, it's common to use GPU cluster that connect many GPIs for parallel and distributed computing. So in that case, low power optical connection using optical chiplet is promising for constructing large clusters. In this example, there are 4 processors, they are adjacent, so neighboring processes are connected electrically. But to build even larger cluster, it's necessary to connect XPU further away. For example, the connection of this unit and this unit. In that case, optical transmitter, which is attached here, processor is the solution. We believe that the optical connection has advantage in such configuration. And even when connecting large board to another large board, the communication is controlled using optical switches. Large clusters can be also considered by utilizing the characteristics of optical connections in which the power consumption is not almost increased with distance. Okay, that's all. That's all my presentation. Thank you for your attention.
Thank you very much. Is there any question on the floor? Okay, yes.
Thank you for a very interesting presentation. I have one question about silicon photonics-based DRX you mentioned as PEC-1. I want to know, maybe this PEC technology can expand the analog bandwidth rather than the divided case between coherent DSP and devices. How much analog bandwidth it can realize at current technology?
Sorry, I have currently no specific value at this moment, so must answer for at this time. Sorry.
Thank you.
Any other question from the floor? I'm very curious about the one question I didn't make. So PEC-4 and PEC-3 and PEC-4, it's a very quite challenging technology, I believe. So instead of using internal, tiny gold transmission line, you are using this fiber optic technologies transmission system in the IC. So I'm quite wondering, for instance, a current single mode fiber core is around 9 micrometer, for instance. But if we have this kind of diameter limitation, we cannot reduce the size of IC anymore. So is there any restriction to employing this kind of technology in the IC?
Yes, I also think that there's some limitation of size for the single mode fiber, but in our application, the PEC is used for enlarge the scales of the link. So I think in that case, the size of this kind of size is not so problem.
This current CPU, for instance, they are employing not a nanometer. It's moved into a more small size line width they employing. So this kind of technological evolution we can expect by using these ion technologies also.
Maybe I'm not sure, but I hope so.
Okay, thank you very much. So any other question on the floor? Okay. Okay, thank you very much. Thank you very much.